So far, we have found the center of mass in a one-dimensional system, if we're thinking about just like a seesaw. We have also found the center of mass in a two-dimensional system, if we're thinking about points in a plane with different varying masses. And now, finally, we're going to be looking for the center of mass of a planar lamina. So when we're finding the center of mass of a planar lamina, we're thinking about a plane region in the xy axis. So we'll be given the graph of functions or a single function, and that will determine a region, and we're looking for the balancing point of that region to calculate the center of mass of that region. You will see us refer to the center of mass as synonymous with the centroid. We'll use these formulas to help us calculate that. So starting in example 4, we're looking for the center of mass of the lamina of the uniform density, rho, bounded by the graph of f of x is equal to 4 minus x squared and the x-axis. I begin by just sketching the region 4 minus x squared. It is a parabola that opens downward that has been shifted up 4. It is this region here. So if I'm looking for the center of mass of that region, hopefully we can see that the center of mass has to be on the y-axis. So I definitely know that x bar is equal to 0. What we don't know is y bar. We will also calculate and verify that x bar is equal to 0, but just from looking at the region we can see that. So to calculate the center of mass, this point x bar and y bar, we need three things. We need capital M sub x, the moment about the x-axis. We need capital M sub y, the moment about the y-axis. And we need little m, the mass of the entire lamina. We begin by calculating M sub x, the moment about the x-axis, which according to the formula here, is equal to rho multiplied by the integral from a to b. Our a and b are -2 and 2. We can see that by setting our parabola equal to 0 to find the x values that bound this region. So we have our limits on our integral. And then on the inside of the integral, we have f plus g divided by 2. F is the function that bounds the top of the region, and g is the function that bounds the bottom of the region. So our f is the parabola. So for f plus g, for f we have 4 minus x squared. And then we add g. G is just 0 because we are using the x-axis, so we do not need to add g. And then we will divide that by 2. And then that is multiplied by f minus g. Again, f is 4 minus x squared, and g is 0, so we don't have anything to subtract from it there. We can simplify this by bringing out the constant of 1/2 from the division by 2 in the denominator, and then we are left with integrating the product of 4 minus x squared times 4 minus x squared. That would need to be FOILed out before the power rule for integration can be applied. And once we apply the power rule for integration, we will have 16x minus 8x to the third divided by 3 plus x to the fifth divided by 5. And we will evaluate that from -2 to 2 to get 256 divided by 15, and that's still multiplied by rho. Now we go on to calculate the moment about the y-axis using this formula here, where that is rho multiplied by the integral from a to b, which is still -2 to 2, x on the inside of the integral multiplied by f minus g. Well, our f is 4 minus x squared, and our g is 0. So to calculate the moment about the y-axis, we are integrating 4x minus x cubed. So I'll go ahead and apply the power rule to integrate this, and then we will evaluate this. I dropped my rho from -2 to 2 to give us 0. Now that we have the moment about the x-axis and the moment about the y-axis, the last thing we need to calculate is the mass of the lamina, which is equal to rho times the integral from -2 to 2 of f minus g. And f is 4 minus x squared, and we do not need to subtract g because it's simply 0. So we have rho multiplied by, I begin to integrate and get 4x cubed. I get 4x minus x cubed over 3, which will be evaluated from -2 to 2 to give us 32/3 rho. So now with all three of these pieces, we are able to calculate the x-coordinate for the center of mass, which is equal to the moment about the y-axis divided by the mass of the lamina. So that's 0 divided by 32/3 rho, confirming that the x-coordinate for the center of mass is 0. And now let's go calculate y bar, the y-coordinate, which is equal to the moment about the x-axis divided by the mass. So that is 256 divided by 15 rho divided by 32/3 rho. Notice that these rows cancel out. We'll talk about that in a second, leaving us with 8/5 for the y-coordinate. And so our final answer is that the center of mass of this region is the point 0, 8/5. That is that point right there, the balancing point of that region. So you'll notice that these densities here canceled out. And that's always going to happen in these formulas. So what it turns out to be is that the density does not affect the center of mass. It only depends on the shape of the region. It only depends on what the function f and what the function g were, as long as the mass is uniform. And we will always be assuming a uniform mass in our regions. So since density does not matter, we will assume that rho is equal to 1. So I'm not going to be writing rho in these formulas anymore. When we calculate other centers of masses or other centroids, remember that center of mass can be used synonymously with centroid, because we're just going to assume that rho is equal to 1. Well, let's look at this formula here for the mass of the lamina. If rho is equal to 1, then that doesn't really matter. And this is simply the area of the region. This goes back to section 7.1 where we were finding the area of a region. So now let's apply that to example 5. We have two graphs, a parabola and a line. I will first start by sketching them. That's the same parabola that we worked with earlier. Has x-intercepts at -2 and +2, and has been pushed up 4 to the point 0, 4. Now we're introducing the line g of x is equal to x plus 2. That's a line with slope 1 that has been pushed up 2, and so that line looks like this. So what we're going to need to know is we're going to need to know the points of intersection. I can see one point of intersection here at -2, 0. I'm not sure what exactly that other point is right there. To find it, I'm going to set these two functions equal to each other, and I'm going to solve for x. This is a quadratic equation. It is the equation x squared plus x minus 2 is equal to 0. This can be factored into x plus 2, x minus 1 equals 0 to tell me that my points of intersection are at -2, which we already knew, and +1. So this is the point +1, and we could conclude that the y-coordinate is 3 just by plugging it into that line. So now we know what our limits of integration would be. They would be from -2, this x value, to 1, that x value, since we're working with this region here. Let's start off and find just the area of this region. It really doesn't matter which one we find first. We're still going to need the moment about the x-axis, the moment about the y-axis, and little m. But remember that since we are assuming that rho is 1, little m is simply the area of this region. So going back to 7.1, if we were asked to find the area of this region, we would integrate it from -2 to 1 of the top function, which is the parabola, 4 minus x squared, minus the bottom function, which is the line x plus 2. And we do need to make sure to wrap that in parentheses so that we distribute the negative. So we have the correct integrand of 2 minus x minus x squared. So we integrate each term and apply the fundamental theorem of calculus to get that the area of this region is 9/2. So now let's go on to calculate the x-coordinate for the center of mass. The x-coordinate for the center of mass is the moment about the y-axis divided by the area. Before we were writing the moment about the y-axis divided by the total mass, but the total mass is simply the area of the region. So to calculate the moment about the y-axis, we are going back to using this formula here, when I'm not going to be writing rho. So I'm just going to have x multiplied by f minus g on the inside of my integral. And my limits are still from -2 to 1. So we have x multiplied by f minus g on the inside of our integral. F is still the function that is on top, which in this case is the parabola. And from that we subtract g, which is the function that's on the bottom, which is the line. So when we simplify, we need to distribute this negative, and then all of this is still multiplied by x. On the inside, one thing I am missing here is I said that I was going to go ahead and calculate the x-coordinate, which means I need to be dividing by a. I don't have that division by a on the inside of that integral, and so I'm going to add that in. So if I want to divide by a, I'm dividing by 9/2, which means I'm multiplying by 2/9. So this division by a is captured by me putting that 2/9 in front. So this integral simplifies to 2/9. Simplifying on the inside, we would get -x cubed minus x squared plus 2x. Please do take the time to go through that algebra on the inside of that integral and make sure that you're getting the same thing that I'm getting. Here I am using the power rule for integration, and I will now apply the fundamental theorem of calculus to conclude that the x-coordinate for the center of mass is -1/2. Now I will go on to calculate the y-coordinate for the center of mass in a similar manner. I'm going to calculate the moment about the x-axis, and I'm going to divide that by a. Since I'm dividing by a, I will be multiplying by 2/9. The limits of integration are the same, and to calculate the moment about the x-axis, we are now using this formula here that I am highlighting in blue. Remember that we are assuming rho is equal to 1. So on the inside of our integral, we have f plus g. That's the parabola plus the line, all divided by 2. And then that's multiplied by f minus g, which is the parabola minus the line. So we have to be careful here on the inside of this integral with simplifying this expression. I will go ahead and pull out this division by 2 in the front of the integral, which will cancel this 2 right here and just leave me with a 1/9 in front of the integral from -2 to 1. When we simplify everything on the inside of the integral, we should end up with x to the 4th minus 9x squared minus 4x plus 12. Again, please do take the time to go through that algebra. All of this is just addition here, so you can just drop parentheses and combine like terms. You need to distribute this negative on the inside of these parentheses, and then these two factors need to be multiplied together. Now I will go ahead and integrate. And I will evaluate this from -2 to 1 to get the y-coordinate for the centroid, where the center of mass is 12/5. So our final answer is that the centroid of this region is -1/2, 12/5. In our last example, we will see that when we're working with simple regions, we do not need integration in order to find centroids. So we want to find the centroid of this region here, and we can think of this region as being subdivided into three separate regions. This region here in red, the region in the middle in blue, and then finally the rectangular region on the right side in green. And the problem gives us the individual centroids of each of those three regions, but I want to talk for a second about how to find them. So starting with the red region here, if we know that it has a width of 1, then directly in the middle of that would be 1/2. And if we know that it has a total height of 3, then directly in the middle of that would be 1.5. And so the centroid for that first region is at 1/2, 3/2. So we think of superimposing this onto the XY plane, where this is just sitting on the x-axis and that's lined up against the y-axis. So for example, this blue region here, remember that this was 1. They tell us that this goes over 3, so this ends at 4. So the centroid for this blue region is going to be directly in the middle of 1 and 4. The point that's in the middle of the x value of 1. This is the 1 here. 1 and 4. Well, 1 plus 4 is 5, and if we take 5 and divide it by 2, we land at 5/2. I just averaged them to find the middle. Again, I know this height right here only goes up to 1, and so halfway up that would just be 1/2. So we find the centroids of these regions by just finding the midpoint of each subsection that we break it up into. And once we have those midpoints, those centroids of the individual regions, we can use all of them to find the total centroid of the entire region. Keep in mind that we will need the total area of the entire region. That's that's similar to when we need the entire area of the plane region when we're working with the planar lamina. So to get this area, I'm going to add up the area of each of these rectangles. The first rectangle is 3 by 1, so it has an area of 3. The second rectangle is blue, is 1 by 3, so it also has an area of 3. And the final rectangle in green is 2 by 2, and so it has an area of 4, giving us the total area of the region to be 10. So now that we know the total area of the region, let's go on to find x bar, which is going to be the x-coordinate for the center of mass. We know that that x bar is the moment about the y-axis divided by the total area of the region. Moment about the y-axis divided by the total area of the region. To find this moment, we do not need to use integration if we're working with a simple region like this. So we do know that the total area of the region is 10. Then to find the moment about the y-axis, we're going to break this up into the three regions that we're working with. Starting with the first region here in red, we know that its centroid is the point 1/2, 3/2. We take the x-coordinate of that centroid. Since we're working with the moment about the y-axis, we're taking x-coordinates of that centroid, and we multiply it by the area of that red region. So this 3 right there, the area of just the red region. Then we'll add and move on to the blue region. We take the x-coordinate from that centroid, which is 5/2, and we multiply it by the area of the blue region, which is 3. And then finally, we take the x-coordinate of the centroid from the green region, which is 5, and we multiply it by the area of the green region, which is 4. Putting all this together gives us 29/10. So I know the x-coordinate of the centroid for the entire region is 2.9. In a similar fashion, I will calculate the y-coordinate of the centroid for the entire region by calculating the moment about the x-axis for each one of these individual pieces. So starting with the red region, we're going to take the y-coordinate of its centroid, which is 3/2, multiply it by the area of the red region. To that we will add the y-coordinate of the centroid for the blue region, multiply it by the area of the blue region, and then we add in the y-coordinate of the centroid for the green region and multiply it by the area of the green region, which leaves us with 10 divided by 10, giving us 1. So now we know that the centroid for the entire region is the point 2.9, 1. I think it is worth noting that if we take all three of these centroids and we average them, we do not get this. So it's not a matter of just taking all these x coordinates, adding them up and dividing by 3 and doing the same with the y coordinates. We actually do have to go through calculating these moments about the y-axis and moments about the x-axis.